Few individuals have left as enduring a mark on the tapestry of scientific and mathematical knowledge as Carl Friedrich Gauss.
Let's take a journey back to 1777 in Brunswick, a small town in Germany. Here, in a humble setting, Carl Friedrich Gauss was born.
From a young age, Gauss showed signs of exceptional brilliance. His father, a treasurer for the Stonecutters Guild, quickly noted the boy's talent for complex calculations.
Anecdotes about Gauss's early mathematical prowess abound, but one story stands out: the summing of integers from 1 to 100. Within seconds, young Gauss had astounded his teacher with the correct answer.
Gauss's solution was revolutionary yet simple, a characteristic that would echo throughout his future work. He grouped the numbers into 50 pairs, each summing to 101. He started with the first number and added it to the last number, took the second number and added it to the second to last number, and so on. Thus, the total was 5,050.
Recognizing his immense potential, the Duke of Brunswick took it upon himself to sponsor Gauss's education. This allowed Gauss to first study at Collegium Carolinum, before moving on to the University of Göttingen.
At the University of Göttingen, Gauss delved deeply into number theory, the study of integers and their relationships. This field, with its simple but complex outcomes, became the playground for Gauss's mathematical creativity.
He indulged in challenging problems involving prime numbers, divisibility, and the nature of numbers themselves. But it was his work on a very particular problem that marked a seminal moment in his early career.
The ancient Greeks, accomplished geometers as they were, had shown that certain regular polygons, shapes with equal sides and angles, could be constructed using only a compass and a straight edge. But since the time of Euclid, this list had remained limited.
The Greeks had found constructions for polygons with 3, 4, 5, and other number of sides, but there is a gap. Regular polygons, whose number of sides were certain prime numbers, such as 17, defied construction.
Yet Gauss, undaunted by the centuries of mathematical giants before him, stepped up to this challenge. He found a way to break the problem down by using the properties of certain types of polynomials, called cyclotomic polynomials.
In 1796, at the young age of 19, Gauss astonishingly proved that a regular 17-sided polygon, or heptadecagon, could indeed be constructed with a compass and a straight edge. This feat hadn't been accomplished since the time of the ancient Greeks.
Gauss's accomplishment not only expanded the list of constructible polygons, but also deepened our understanding of the interplay between geometry and number theory. The seemingly simple act of drawing a shape unveiled a profound connection between different areas of mathematics.
The impact of Gauss's work on constructible polygons can't be overstated. It marked the beginning of a rich period in the study of number theory and set the stage for many of his future contributions to mathematics.
But Gauss's contributions didn't stop at a 17-sided polygon.
That's right, Gauss's journey in mathematics went far beyond geometric constructions. His doctoral thesis, in fact, became a cornerstone of algebra.
In this thesis, Gauss tackled a problem central to algebra, the nature of polynomial equations. These are equations involving variables raised to whole number powers, like x squared minus 3x plus 2 equals 0, for example.
An unsolved question at the time was the behavior of these equation solutions, or roots. Specifically, could we guarantee that every polynomial equation actually had a root, and if so, how many?
Gauss dove headlong into this problem, emerging with a revolutionary proof of what we now call the fundamental theorem of algebra. And contrary to its daunting name, the concept of this theorem is quite straightforward.
The theorem states that every non-constant polynomial equation with complex coefficients has a complex root. This means that no matter what polynomial equation you come across, as long as it's not a constant and its coefficients, or the numbers multiplying the variables, are complex numbers, you can be sure that it has at least one complex root.
But what does this mean? Well, in essence, it means that every polynomial equation has a solution in the complex number system. Remember, the complex number system includes all the real numbers we're familiar with, as well as numbers involving the imaginary unit I, which is the square root of -1.
By proving this theorem, Gauss didn't just answer an open question, he actually established a critical foundation for much of modern algebra. His proof ensured that we could solve any polynomial equation, giving us a reliable tool for understanding and manipulating these mathematical expressions.
Gauss's work on the fundamental theorem of algebra illustrates his extraordinary ability to probe deeply into mathematical theory and come out with insights that reshape our understanding of the field. It's another testament to his enduring legacy in the world of mathematics.
Gauss graduated from university in 1799. 2 years later, Gauss has published his most monumental work, Disquisitiones Arithmeticae, revolutionized the field of numbers theory. Its influence resonates even today, making it a cornerstone of modern mathematics.
Indeed, in his magnum opus, Disquisitiones Mathematica, Gauss delved further into the complex and fascinating world of number theory. This book was a treasure trove of novel mathematical ideas, setting the stage for centuries of further study.
Within the pages of Disquisitiones Arithmeticae, Gauss introduced the world to the concept of congruence, a fundamental idea in number theory even today. But what is congruence, you ask?
Well, simply put, two numbers are said to be congruent if they leave the same remainder when divided by a certain number. For example, 17 and 7 are congruent with 10 because they both leave a remainder of 7 when divided by 10. Gauss introduced the notion and developed a systematic theory around it.
Gauss also introduced the law of quadratic forms. This law allowed him to classify quadratic forms over the integers, which are expressions like ax squared plus bxy plus cy squared, where a, b, and c are integers, and x and y are variables.
Through Disquisitiones Arithmetica, Gauss laid the foundation for the theory of numbers as we know it today. His innovative and comprehensive approach has allowed generations of mathematicians to further explore and expand on these fundamental concepts.
Moving beyond the realms of pure mathematics, Gauss made substantial strides in the field of astronomy and statistics. He devised a method to calculate the orbit of newly discovered asteroid Ceres. His prediction was spot on, leading to the rediscovery of the lost asteroid.
Ceres was first discovered in 1801 by the astronomer Giuseppe Piazzi, but soon after its discovery it was lost, obscured by the sun's glare. Many astronomers attempted to predict its location, but their calculations were off, and Ceres remained lost.
But this was a challenge Gauss couldn't resist. Drawing on his extensive mathematics skills, he devised a new method to calculate Ceres' orbit. Instead of the traditional two-body problem typically used for such calculations, Gauss developed a method to solve the more complicated three-body problem.
The three-body problem involves predicting the motions of three bodies interacting through gravity, which is a far more complex task than predicting the motion of just two bodies. But Gauss's innovative approach allowed him to predict Ceres' orbit with remarkable accuracy.
His method involved the principle of least squares, a technique still widely used in data analysis and curve fitting. In this principle, Gauss could take limited observations available, calculate the possible error, and minimize that error to make his prediction as accurate as possible.
Gauss's predictions were spot on. When astronomers pointed their telescopes to the location he predicted, they found Ceres, right where Gauss said it would be. His achievement not only revealed his genius in astronomy, but also the power of mathematics to predict and explain phenomena in the natural world. His use of the method of least squares in predicting Ceres' orbit paved the way for further development in statistics as well.
That's right. In fact, this brings us to another of Gauss's significant contributions to statistics. He's the namesake of one of the most important concepts in this field, the Gaussian or normal distribution.
The Gaussian distribution, also known as the normal distribution, is another monumental contribution of Gauss to the field of statistics and probability theory. It's so prevalent in the natural and social sciences that you've probably heard of it referred to as the bell curve.
This bell curve describes a pattern that emerges when you gather a lot of data about almost anything. Human heights, standardized test scores, errors in measurements, and so much more follow this distribution.
At the heart of the Gaussian distribution is the concept of randomness. It captures the idea that, in the natural world, values tend to cluster around the average or mean value, and the farther we get from the mean, the less likely we are to find those values.
Mathematically, the Gaussian distribution is defined by its mean, mu, and its standard deviation, sigma. The mean indicates where the center of the peak of the bell curve is, while the standard deviation controls how spread out the curve is.
Over time, the Gaussian distribution has proven to be incredibly useful in a wide variety of fields, including physics, engineering, computer science, finance, and even in social sciences.
It is one of those mathematical concepts that beautifully captures a recurring pattern in nature, further testament to Gauss's profound insights and far-reaching contributions.
Gauss's enduring curiosity also led him to make significant contributions to the field of geodesy, a branch of applied mathematics concerned with the Earth's shape and dimensions.
In 1818, Gauss embarked on a mission to survey the Kingdom of Hanover. His role in this endeavor was instrumental, and it led to the development of the Gauss-Kruger coordinate system, still used in geodesy.
Gauss was not one to shy away from inventiveness. During the survey of Hanover, he invented the heliotrope, an instrument that reflects sunlight over long distances to measure angles accurately.
The underlying principle of the heliotrope was pretty straightforward. It was essentially a mirror mounted on a precise and adjustable stand. The mirror could be turned so that it reflected the sun's light in any desired direction.
Gauss ingeniously used the heliotrope as a surveying tool. By setting up heliotropes at specific points, he could have an observer at different locations look for the flash of reflected sunlight. The line from the observer to the heliotrope then formed one side of a triangle.
And here's where it gets interesting. By repeating this process with different pairs of points, Gauss could form a network of triangles covering the area he was surveying. The angles of these triangles could be measured very accurately with the heliotrope, and since the distance between at least one pair of points was known, the lengths of all the other sides could be calculated using trigonometry.
This method, known as triangulation, was the basis of the surveying process. And the heliotrope, with its ability to reflect sunlight over very long distances, made it possible to measure angles more accurately than ever before.
So, through his work on the Survey of Hanover, Gauss made significant contributions to the field of geodesy, and his inventions like the Gauss-Kruger coordinate system and the heliotrope continue to influence the field to this day.
Moving beyond the Earth's surface and the celestial realm, Gauss left an enduring legacy in physics, particularly in electromagnetism. Alongside the physicist Wilhelm Weber, he developed what we now know as Gauss's law, a key principle in understanding electric flux through a given area.
Gauss's law is foundational in the study of electromagnetism, underscoring Gauss's significant contributions not just in mathematics, but across multiple scientific disciplines.
To understand Gauss's law, we need to understand a few concepts. The first is electric field, a region around a charged particle within which a force would be exerted on another charged particle. The second concept is electric flux, which is essentially a measure of the number of electric field lines passing through a given area.
Now, Gauss's law relates the electric flux flowing out of a closed surface to the charge enclosed by that surface. In simpler terms, it says that the total outflow of electric field from a volume is proportional to the total electric charge within that volume.
This might sound quite abstract, but it's fundamentally crucial in understanding how electric fields behave. For example, it explains why the electric field inside a conducting shell is zero when the shell has no net charge inside it, regardless of any charges outside the shell. It's principles like this that underpin our understanding of electrostatics.
And let's not forget that Gauss's law is one of Maxwell's 4 fundamental equations of electromagnetism, which together describe how electric and magnetic fields interact. They're the foundation of our modern understanding of electromagnetism, and you'll find them at the heart of everything, from the humble electric motor to advanced quantum field theory.
Despite his academic output, Gauss was known to be highly critical of his own work. He adhered to the motto pauca sed matura, few but ripe. This led him to only publish when he was fully satisfied with the perfection of his work.
Even as Gauss aged, his desire to understand the intricacies of the world around him never waned. He continued to remain active in the scientific community, contributing to a variety of fields.
Indeed, in his later years, Gauss had become interested in geophysics and did pioneering work on the study of terrestrial magnetism. He developed a comprehensive theory of Earth's magnetic field and made several key observations.
In 1831, he founded the Göttingen Magnetische Verein, or Magnetic Union, together with Wilhelm Weber. This organization collected magnetic data from all over the world. Their observations and research resulted in a better understanding of the Earth's magnetic field and its variations.
Throughout his life, Gauss also mentored several students who would go on to become distinguished mathematicians and scientists themselves. His influence, both through his direct teachings and through his extensive body of work, has had an enduring impact on various fields of science.
As he neared the end of his life, Gauss continued to be honored for his contributions to science. He was recognized by several scientific societies, and his work continued to inspire researchers around the world.
Gauss passed away in 1855, though his legacy continues to shape the scientific and mathematical world. His impact is seen in every field, from number theory and geometry to statistics, magnetism, and physics.
As we reflect on Gauss's life, we marvel at the brilliance of his mind, the breadth of his contributions, and his enduring impact on our understanding of the universe.